Hi everyone, so in this video we're going to take a look at some material in chapter 7 which deals with existence proofs, and then towards the end we'll take a look at some material in chapter 9 which deals with disproof. So up until now we have been focused on mostly proving conditional and biconditional statements, if this then that, and we've learned various proof techniques for conditional statements. Let's now consider how would we prove an existentially quantified statement, meaning a statement that has a there exists in it. So for example, let's say we wanted to prove that there exists injective functions f and g that are both going from R to R such that their sum is not an injective map from R to R. And we actually took a look at this in class last time. So how could we prove this statement? Well, first of all, this is what is called an existence statement, or if the result is more significant, we would call this an existence theorem. And to prove such a statement or theorem, all we have to do is provide one concrete example that shows that it is true. And so a proof of this example is given below, where we now have produced a concrete example, namely we set f of x equal to x, g of x equal to minus x, and we have shown that the statement is true, that in fact, when we add these two together, we can get a non-injective function going from R to R. So that would be a complete existence proof for that statement. We only need to provide one concrete example. And so the proof that we just had for the statement about the sum of two injective functions not necessarily being injective would be an example of a constructive proof of this existence statement. So here we've actually given an explicit example that proves this statement. We could also have what's called a non-constructive proof for this existence statement, where we prove that such objects exist without actually stating them. And so an example of a non-constructive proof for the previous example, which was there are two injective functions whose sum is not injective, we could also have proven it this way by keeping it a little bit more general. So let's just let f be any injective function, and then we're going to define g of x to be minus f of x. And so we haven't actually constructed concrete examples for f and g, but we've shown that for any injective map f, we can construct an injective map g so that the sum of those two functions is not injective. So really, this is a generalized proof of the concrete example that we constructed previously. Both of these are totally valid proofs for the existence statement that we looked at on the previous slide. And changing gears slightly from existence proofs, we've been focusing on here's a statement P, let's prove that it's true. And oftentimes what we might be asked to do is show that a certain statement is false. And this is what is called disproof. So for example, if we want to disprove the following statement that for any x in the positive reals, that's what this is representing, x is greater than or equal to the square root of x. And this would be an example of what is called disproof. So the process of showing that a statement is false, we call that disproof. And the way that we can disprove a statement P is to show that its negation, not P, is true. So let's see how this disproof would work for this example, where we want to disprove the statement that for all positive real numbers, x is going to be greater than or equal to its square root. So what would that look like? So here, the statement that we're trying to disprove, if I write it out using the universally quantifier, for all x in the positive reals, we want to show that x is bigger than or equal to the square root of x. And we actually want to disprove this statement. And the way that we can disprove this statement is by showing that its negation is true. So let's recall, how do we negate a universally quantified statement such as P? Well, we change the quantifier to an existential quantifier, and then we negate the statement. So in this case, not P would mean that there exists some x in the positive reals for which its square root is larger than x. So in other words, if we can produce one example of an x in the positive real numbers, that makes the original statement false, which in this case would be equivalent to showing that x is less than its square root, then we're done. So we just need to produce one counter example, in other words. So what would such a counter example be? Well, if we were to take x equals 1/4, then 1/4 is less than 1/2, which is the square root of 1/4. And this is sufficient to show that it is not true for all x in positive reals that x has to be bigger than or equal to its square root, because we just gave one example of an x for which this is not true. Okay, so to generalize the discussion from the previous example, if we want to disprove a statement R, then we can prove that its negation, not R, is true. And so if the statement R happens to be a for all statement, such as for all x in some set S, P of x, then we can produce one example of an x in S that shows that P of x is false. And again, this follows from the fact that when we negate this universal quantified statement, we get an existentially quantified statement like this. So that means we want to show that there is some x that is going to make P false, that not P is true. And that would be sufficient. We can also use disproof for other types of statements. So if our statement R happens to be a conditional statement of the form if P then Q, and we want to disprove this statement, then we need to produce an example of an x that makes the conditional statement false. And the only way this conditional statement would be false is if we can produce an x that makes the hypothesis P of x true, but the conclusion Q of x false. So that's how we can apply disproof to conditional statements. We want to produce an x that makes the hypothesis true, but the conclusion false. And we'll see some examples in this in class. And then lastly, we can apply disproof to existence statements. So these would be statements that have an existential quantifier. And so to disprove this, we want to prove that its negation, which would be a universally quantified statement, is true. So we need to show that if x is in S, then it follows for all of these that not P is true. So we'll work with concrete examples of these types of proofs in class. Be sure to take a look at the reading quiz and answer those questions before coming to class.